In a previous section, we talked about limits going to infinity and how we can approach those. So if we were to look at the very first limit, we have the limit as x goes to infinity of 3x plus 5 over 2x minus 1. And normally what we would do is say this is the limit as x goes to infinity of 3x plus 5 over 2x minus 1 times 1 over x because the highest degree in the denominator is 1. So it would just be an x. And when we do that, we end up then with the limit as x goes to infinity of 3 plus 5 over x over 2 minus 1 over x. And we know that 5 over x and 1 over x will both go to 0 as x goes to infinity. So we end up with 3 over 2. Another one was, what is the limit as x goes to 0 from the right of natural log of x over cotangent x? Well, natural log of 0 is undefined. It doesn't exist. And cotangent of 0 is not going to work either because we have 1 over 0. Because remember, tangent is sine over cosine, so cotangent is cosine over sine. So it's cosine of 0, which is 1, divided by sine of 0, which is 0. So here, what we really end up having here is a negative infinity over a positive infinity. And that's not good. So the way we got around this, we said, all right, fine, let's try to find it as we let x go to 0 from the right. Typically, how we handle this is we say things like let x be 0.1. And then we would have the natural log of 0.1 over the cotangent of 0.1, which is negative 2.303 over 9.967, or a negative 0.231. Now, if we let x equal 0.01, we find out that the natural log of 0.01 over the cotangent of 0.01 is negative 0.046, and so on and so on. So the limit as x goes to 0 from the right of the natural log of x over the cotangent of x is actually 0. How did that happen? Well, in the past, we didn't really have an analytic way to look at this kind of problem, but we're going to change that today. We're going to look at a new way to take limits or define limits. And those are limits of a very special kind of result. Those are limits who are indeterminate. That would be your infinity over negative infinity, or negative infinity over infinity, infinity over infinity, and negative infinity over negative infinity. It also includes things like 1 to the infinity, infinity to the 0, 0 to the 0, 0 times infinity, infinity minus infinity. All of these indeterminate. The biggest one that we usually see that we don't know how to handle is the one where we get 0 over 0. And all of those are laid out here. So these are called our indeterminate forms of the type 0 over 0, any kind of infinity divided by another kind of infinity, 0 times infinity, the difference of two infinities, 1 to an infinity, infinity to the 0, and 0 to the 0. Our limit from the second example was negative infinity over infinity, and that was one of the special types of rules we're looking at. So we'll get to that one, but let's talk about different cases for L'Hopital. So what is L'Hopital? L'Hopital's rule uses derivatives to help us find indeterminate limits. So suppose f and g are differentiable functions over an open interval containing a, except possibly at a, if the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is also 0, then the limit as x goes to a of their quotient can actually be found, since it would be 0 over 0, we can also find it by taking the derivative of the numerator over the derivative of the denominator. Notice we did not use the quotient rule. We weren't finding the derivative of f of x over g of x. We're finding the derivative of f of x divided by the derivative of g of x. That is L'Hopital's rule. So this assumes that the limit exists or is plus or minus infinity. It also holds if we're considering one-sided limits or limits at infinity. So what does it look like when we put this into action? And we're going to find out. We have special cases for all of our indeterminate forms. So let's see what it looks like. In the first example here from 4.8.1, we have in A, the limit as x goes to 0 of 1 minus cosine x over x. So if we evaluated it directly, we would get 1 minus the cosine of 0 over 0. So what does direct substitution give us? 1 minus 1 over 0. Well, 0 over 0. Not good. Enter L'Hopital. L'Hopital says, and I know it looks like L'Hopital, but it is L'Hopital. So L'Hopital says then you can change this into the limit as x goes to 0 of the derivative of 1 minus cosine x. And the derivative of negative cosine x is a negative times, and the cosine's derivative is negative sine x. Derivative of x is just 1. So we really end up with the limit as x goes to 0 of sine x over 1, or the limit as x goes to 0 of just sine x. Well, if we did direct substitution, well, that's just the sine of 0, which is 0. And limits just got a lot simpler. And the nice thing is, by the time we get to a cumulative final, you'll have L'Hopital, and you'll be able to use it for some of those forms that we had earlier in the very beginning of the semester that we had to find other tricks to get around. Things where we had to multiply by conjugates of square roots, or we had to do some other sort of trick. So the nice thing is now we've got L'Hopital to help us sort of get around those guys. Let's see what happens when we look at the limit as x goes to 1 of the sine of pi x over natural log x. Well, that would be through direct substitution, the sine of pi over the natural log of 1. Well, sine of pi is also 0. Natural log of 1 is also 0. Again, a sad indeterminate form. Enter L'Hopital. L'Hopital's rule says then this is the limit as x goes to 1 of the derivative of sine of pi x. Derivative of sine is cosine of pi x, but our chain rule says then we also have to multiply by the derivative of pi x, which is pi. Divided by the derivative of natural log of x is 1 over x. And so could we go ahead and simplify this? Absolutely. We don't really have to, but I'm going to. So the limit as x goes to 1 here would then be pi x times the cosine of pi x, which means we have pi times 1 through direct substitution, the cosine of pi. Well, that's pi times, well, the cosine of pi. Remember that pi is the same as 180 degrees. So on our unit circle, right, pi is back here at -1, 0. Remember, we have cosine theta, sine theta are ordered pairs. So here our cosine is -1. So we get pi times -1, or negative pi. Not something we could have guessed would be our limit. Okay, let's see if we can keep trucking here with our L'Hopital's rule. L'Hopital makes very quick work of a lot of derivatives, or sorry, a lot of limits. It's such a handy tool to have. You're going to try to use it on every limit. Just make sure you try direct substitution first to make sure that L'Hopital's rule applies. Because when you try direct substitution, if you can evaluate the limit, you cannot use L'Hopital's rule. You have a limit. It's not of an indeterminate form. So every time that you want to evaluate a L'Hopital rule, you have to make sure that your limit is actually of an indeterminate form of those ones listed on the first page. So that's why we're doing it every time. So the limit as x goes to infinity of e to the 1 over x is going to be e to the 0, and then minus 1 over theta, or sorry, 1 over x is going to go to 0. 1 minus 1 over 0, or 0 over 0. Indeterminate, not good. Enter L'Hopital's rule. We need to do a little bit of simplifying some of our expressions before we can really take the derivatives. So let's say this is our limit as x goes to infinity, and e to the 1 over x is the same as e to the x to the minus 1, and its derivative would be e to the x to the minus 1 times the derivative of x to the minus 1. That is our chain rule for exponentials. And we'll divide it by 1 over x is also x to the minus 1. So a really interesting thing happens. We could cancel out those derivatives of x to the minus 1 right there. But I'm going to go ahead and evaluate it because we could always use the extra practice. So we end up with the limit as x goes to infinity of e to the x to the minus 1 times negative x to the negative 2 divided by negative x to the negative 2. And now we certainly can cancel these guys, and we end up with the limit as x goes to infinity of e to the x to the minus 1, which if we rewrite it back to the way we started, is e to the 1 over x. And when we let x go to infinity, we get e to the 0 or 1. So this huge problem with all of these crazy negatives comes down to 1. Now the next question asks, what happens if I take those derivatives and my limit is still indeterminate? Take another one. Try it again. If you find that you're getting into something cyclic and things aren't canceling, L'Hopital may not be the way to go. You may have to find another approach. So if you had a bunch of sines and cosines over top of one another, you might have to find a different way because L'Hopital may not work. And we have sine on the numerator, but we don't have cosine in the denominator or some other trig function, so we might be okay doing L'Hopital here. Let's just try it and see what happens. There we go. All right. So if we plug in 0, we get sine of 0 minus 0 over 0 squared, or 0 over 0, not good. We need L'Hopital. Okay, L'Hopital to the rescue. We now have the limit as x approaches 0 of. Derivative of sine is cosine, minus derivative of x is 1, over the derivative of x squared, which is 2x. Okay, let's try it again. Cosine of 0 minus 1 over 2 times 0. 1 minus 1 over 0 gives us 0 over 0. Still indeterminate. But notice if we take one more derivative of the denominator, the x is going to go away. So let's try it. Let's see what happens when instead we take one more derivative. So we do L'Hopital one more time. Well, now we have the limit as x goes to 0. Derivative of cosine is negative sine x. The derivative of negative 1 is just 0, so that's gone. Over our derivative of 2x is just 2. And now when we let x go to 0, we have the negative sign of 0 over 2, or a negative 0 over 2, which is just 0. So we got there in the end, but we had to go through L'Hopital twice. That's okay. So if you can see that you've got a polynomial where the x's will eventually cancel out and you won't have to worry about having 0 divided by 0 or infinity divided by infinity, then you can keep taking those derivatives and you'll eventually get to the right answer. Let's look at another case. We looked at the indeterminate form of 0 divided by 0. What about the indeterminate form of some form of infinity over infinity? So now f and g are differentiable functions over the open interval containing a, except possibly at a. And we know then that if the limit as x approaches a of f of x is plus or minus infinity, as is the limit as x goes to a of g of x, then the limit of their quotient as x goes to a can be found as the limit as x goes to a, the quotient of their derivatives. And this boils down to exactly the same L'Hopital we saw on the first page. Let's start by revisiting the two limits that we started with in this section. So if we look at the limit as x goes to infinity of 3x plus 5 over 2x minus 1, if we don't do our trick where we multiply by 1 over x on the numerator and the denominator, we would end up basically with 3 times infinity plus 5 over 2 times infinity plus or minus 1. Which would really just be infinity over infinity, indeterminate, not good. So enter L'Hopital's rule. L'Hopital's rule says then this is the limit as x goes to infinity of the derivative of the numerator is 3, derivative of the denominator is 2. There are no x's to let go to infinity. The answer is just 3 halves. So it is just a quicker way to get to the same answer. You can still do your 1 over x trick if you want to. I'm just showing you that you don't absolutely have to now. Let's try instead our limit as x goes to 0 from the right of the natural log of x over the cotangent of x. And we already know this is a negative infinity over a positive infinity derivative. So sad face, it's not going to work. So let's try our L'Hopital rule. So this will be our limit as x goes to infinity. It goes to 0 from the right to many infinities of the derivative of natural log of x, which is 1 over x, divided by the derivative of cotangent. And remember, because it has co in the name of it, we're going to have a negative. So we'll have a negative, and the derivative of cotangent is going to be cosecant squared x. So remember, the derivative of tangent is secant squared, which means cotangent would be a negative and cosecant squared. So we end up then with our limit as x goes to 0 from the right of 1 over x over negative cosecant squared x. So let's see here. If we do a little simplifying, that is x, limit as x goes to 0 from the right, well, that would put the x in the denominator, and cosecant is 1 over sine. So that would be the same as putting the negative sine squared in the numerator. So now let's see if we can evaluate it at 0. So we get negative sine of 0 squared over 0. Okay, so we get 0 over 0, which is indeterminate. But notice what will happen if we take the derivative of the denominator again. It will become 1. So we are going to take one more derivative here. We're going to use L'Hopital's rule one more time. And say, fine, then let's take the limit as x goes to 0 from the right of now a negative 2 sine x times the derivative of sine, which is cosine x, and the derivative of x is just 1. So when we do this and we do our direct substitution, we get negative 2 sine 0 cosine 0 all over 1, we get -2 times 0 times 1 divided by 1, which is just 0, which happens to be the answer that we found essentially by making a table without putting it in a table. So, not so bad. And remember what I said about how you have to always make sure that L'Hopital applies? Let me give you an example of one where L'Hopital doesn't apply. So let's consider the limit as x goes to 1 of x squared plus 5 over 3x plus 4. Well, let's see here. Our limit as x goes to 1 of x squared plus 5 over 3x plus 4. Step 1 is always direct substitution. So that'll be 1 squared plus 5 over 3 times 1 plus 4. This does not look like a 0 over 0 or an infinity over infinity. To me, this is 6 over 7. This is not an indeterminate form. So L'Hopital's rule does not apply. Again, this is also part of if we test this on a quiz or an exam or the final, you would have to show, for full credit, you have to show that it is an indeterminate form first before you apply L'Hopital's rule. So let's talk about a little bit about these last ones. It says for the remaining indeterminate forms, we will need to rewrite the given functions as rational expressions by using algebraic skills and properties before we apply L'Hopital's rule. Well, let's see why we might need to do that. If we evaluated the limit as x goes to 0 from the right of x natural log of x, we get 0 times the natural log of 0, or 0 times negative infinity. That's not going to work. That is one of our indeterminate forms. But you notice this is not a quotient. It is not a rational function, so we have to make it one. So instead, we're going to rewrite it. We're going to now rewrite this as the limit as x goes to 0 from the right. And we're not really going to be moving the natural log. We'll leave it alone, the natural log of x. However, we can put the x in the denominator by dividing by its reciprocal. We'll make it 1 over x. And now when we evaluate this one directly, we get the natural log of 0 over 1 over 0. Or negative infinity over infinity. L'Hopital's rule applies. So let's try it. Let's see what happens. Now we again get the limit as x goes to 0 from the right, and the derivative of natural log of x is 1 over x. In the denominator, we already have a 1 over x, which is x to the minus 1, so we'll be dividing by the derivative of x to the negative 1. So we get the limit as x goes to 0 from the right of 1 over x divided by negative x to the negative 2. Or the limit as x goes to 0 from the right of 1 over x times, well, we'll say divided by, we'll do the keep switch flip, divided by negative 1 over x squared. So we'll keep switch flip on this guy and we'll say that's the limit as x approaches 0 from the right of 1 over x times x squared over negative 1. And that's going to make our lives a lot simpler because now we have the limit as x goes to 0 from the right of x squared over negative x. And when we simplify that, that's the limit as x goes to 0 from the right of just negative x, which is 0. When you do direct substitution, it becomes 0. So our limit then, in the end, our limit as x goes to 0 from the right of x natural log of x truly is 0. So that's our full solution. Pretty cool how L'Hopital can help us get out of some pretty tight spots. Let's see if there's a way in this first problem from example 4.8.5 where we can take an indeterminate form we haven't really found really stated a L'Hopital rule for, and see if we can rewrite it into a form that we recognize. So let's try direct substitution here. We would get 1 over 0 squared minus 1 over the tangent of 0, or infinity minus infinity. And the question is, why is this not immediately 0? Because you don't know the magnitude of each of those infinities. One of them could be a number that's approaching negative 500 billion trillion, and the other one could be something smaller, or it could be vice versa, or we just don't know. We don't know what the magnitudes of our infinities are, so they're themselves an indeterminate form. They are not finite, which is why they're called infinite, infinite, hence the name infinity. So we can't quantify what their difference would be. So let's try instead to rewrite our function. So let's rewrite. Let's see here. Then we would have the limit as x goes to 0 from the right. And let's put it all together in one rational function that has x squared tangent x on the denominator. That means we'd have 1 times tangent x here, which is just tangent x, minus 1 times x squared, which is x squared. Now if we evaluate this one directly, we would get tangent of 0 minus 0 squared over 0 squared tangent of 0, or 0 over 0, which is indeterminate, so sad face, we can't find this limit yet, but now we know L'Hopital applies. So let's see what happens when we use L'Hopital. Well, we'll still have our limit as x goes to 0 from the right. Derivative of tangent is secant squared x minus derivative of x squared is 2x divided by, well, now comes the fun part. We're going to need to use our product rule in the denominator. So x squared, derivative of tangent is secant squared x plus tangent x times the derivative of x squared, which is 2x. So if we were to plug this in, we could say that we have now secant squared of 0 minus 2 times 0 over 0 squared secant squared of 0 plus tangent 0 times 2 times 0. So we end up here with, well, 1 minus 0 over 0 plus 0. Because remember, secant is 1 over cosine. The cosine of 0 is 1. So we get 1 minus 0 is 1. And that means we have 1 over 0, which is infinite. And the denominator here is positive as x goes to 0 from the right. So that's something really important to keep in mind here. Why it goes to positive infinity, and this is because the denominator, right? The denominator is greater than 0. It's positive when x is approaching 0 from the right. So we would get 1 over positive numbers that are approaching 0. So it would be a positive over a positive infinity. So we would say then that our limit as x goes to 0 from the right of 1 over x squared minus 1 over tangent x, and those really should have parentheses around them, is indeed infinity, which was probably not the solution you expected when we saw an infinity minus an infinity? Like I said, we can't quantify it, so we don't know what that difference is. How about the limit as x goes to 0 of x to the 1 over x? Well, this is going to be interesting because we have to come up with a different way to handle it. So here, let's talk a little bit first about direct substitution. We have a limit then as x goes to infinity of x to the 1 over x is going to give us infinity to the 0. That is one of our indeterminate forms. So L'Hopital's rule does apply here. But we might need a little bit of help getting there because, right, it's because it applies, but how? Because we don't have, right now we don't have a quotient. This is where some of our tricks from differentiation are going to help. If you remember, when we have x to the 1 over x, when we want to find its derivative, we use logarithmic differentiation. Well, we're going to find a similar approach here is going to help us find the limit here. So let's let y equal x to the 1 over x. Then we know that the natural log of y is going to be 1 over x, the natural log of x. And then we can say the limit as x goes to infinity of the natural log of y, right, is the same as the limit as x goes to infinity of the natural log of x over x, which in this case would be negative infinity over infinity. And that is another one of our indeterminate forms. Oops, sorry, it's not 0, it's infinity, so this is positive. But it's positive infinity over infinity. That is one of our indeterminate forms. It is a rational function, so now let's do L'Hopital. This is where things can get really interesting. Because if we look at just the left-hand side, right, we have the natural log of y. On the right-hand side, we have natural log of x over x. So here's the kind of cool thing, is that we know, if we apply L'Hopital here, find a color, there we go. We can say the limit as x goes to infinity of the natural log of y, right, is equal to now the limit as x goes to infinity. And let's apply L'Hopital. The derivative of natural log of x is 1 over x. And the derivative of x is 1. And as this goes to infinity, we find out that our right-hand side here is going to be 0 over 1, which is 0. So then we know that the limit as x goes to infinity of the natural log of y is 0. Isn't that interesting? So now, if we move the natural log outside and we say the natural log of the limit as x goes to 0, or sorry, as x goes to infinity of y, it now equals 0. And the way we can rewrite that is that the limit as x goes to infinity of y is equal to e to the 0, which tells us that the limit here as x goes to infinity of y is e to the 0, which is 1. And remember, what does y stand for? x to the 1 over x. So we can say then that the limit as x goes to infinity of x to the 1 over x is 1. So a very tricky way to get around it, but it's using some of the tools we've already learned in other sections. And we have one last problem. And this one is the limit as x goes to 0 from the right of x to the sine x. So let's try it. That would be 0 to the 0, which is indeterminate. But we don't know how to apply L'Hopital here yet. Okay, then we're going to say same bit as before. Okay, let y equal x sine x, or x to the sine of x. Then the natural log of y is going to be the sine of x times the natural log of x. Gotta love those properties of logs. They really help us out. And then what happens is the limit as x goes to 0 from the right of the natural log of y is going to equal, right, the sine of 0, which is 0, times the natural log of x as 0. Okay, so that's negative infinity. So it's 0 times negative infinity. So that's an issue. So, okay, but still we have a product, not a quotient. So how am I going to apply L'Hopital? Well, we got to get to rewriting again. So let's try rewriting one more time here. Of course, the last problem has logarithmic substitution or manipulation, and we have to rewrite it. Right? It just wouldn't be one of my problems if they didn't. So let's try rewriting it here. Let's say then if the natural log of y equals sine x natural log of x, what if we instead, so the natural log of y is, we're going to leave the natural log of x in the numerator, and then do 1 over sine x in the denominator. So we get the natural log of x over 1 over sine is cosecant. Once we do that, then the limit as x goes to 0 from the right of the natural log of y is going to be the limit as x goes to 0 from the right of the natural log of x over cosecant x, which is 1 over sine. So we're going to get negative infinity over infinity. So there is our unhappy indeterminate form, but we can use L'Hopital's rule because now we have a quotient. Whew, so much work. Let's get to L'Hopital here. So we would say then that our limit as x goes to 0 from the right of the natural log of y is now the limit as x goes to 0 from the right of. The derivative of natural log of x is 1 over x. Derivative of cosecant. So remember, secant is secant tangent. So cosecant would be a negative because it has co, and it would be cosecant cotangent. So we end up with negative cosecant x cotangent x. So we can write things out just a little differently here. Because if we change all of these to sines and cosines and move the x to the bottom, let's see what happens. So this is the limit as x goes to 0 from the right of 1 over, and then we have x, negative x. Cosecant is 1 over sine. And cotangent, so tangent is sine over cosine, so this would be cosine over sine. So really, I have, right, the reciprocal of negative x cosine x over sine squared x. So I can rewrite this as the limit as x goes to 0 from the right of the sine squared x over negative x cosine x. Ooh, that's a lot. But if we simplify it just once more, we'll have the limit as x goes to 0 from the right of sine x over x, and then we'll have a sine x over a negative cosine x, right? A negative sine x over cosine x, which is tangent. So we're almost there. This is the limit as x goes to 0 from the right of sine x over x times a negative tangent. Ooh, that's a lot. So this is now the limit as x goes to 0 from the right of sine x over x times the limit as x goes to 0 from the right of a negative tangent. And this is where our rules from derivatives apply and where we have to remember that the limit as x goes to 0 of sine x over x is one of those special limits that we looked at in the beginning of our semester. So that one goes to 1. And the limit as x goes to 0 of tangent, which is sine over cosine, is 0 over 1. So this is going to be a 1 times 0, or 0. So in the end, we have now the natural log of the limit as x goes to 0 from the right of y is 0. So it's the same thing we had before, which means then that we have the limit as x goes to 0 from the right of y is now e to the 0, which tells us that our limit as x goes to 0 from the right of our x to the sine x is 1. So it follows along from the last problem in exactly the same way. So remember to always, definitely always make sure that L'Hopital rule can be applied. If you do not have a quotient of zeros or infinities, get creative in ways to rewrite the problem so that you do have an infinity over infinity or 0 over 0 so that you can apply L'Hopital with the derivatives.